Okay, so we're dealing with a diffraction grating here, and the way these suckers work is that you got light incident normally on the diffraction grating, and then it bounces off in such a way that the blue light and the red light bounce off at different angles, and you got multiple orders of the spectrum, like this. Okay, so this would be the first order, this would be the second order. Okay, now blue light, the wavelength of blue light is 400 nanometers, and the wavelength of red light is 700 nanometers. And what we're interested in is the red end of the second order maximum, and we're told that this angle that the red end makes with the second order is 34 degrees. Alright, now our formula for diffraction grating is that this angle d sine theta, right, where d is the separation between the lines, d sine theta is equal to, in this case, 2 lambda, because we're in the second order. Okay? So we got d sine 34 is equal to 2, and we're interested in the red light. So if I solve for d, I get 2.5 times 10 to the minus 6 meters, which is 2.5 times 10 to the minus 4 centimeters. Now if I want the line density, n, the number of lines per centimeter, that's just 1 over d in centimeters. So that's 4,000. Okay, so there's part 1, or part A of this. Okay. Part B, they want to know how many complete orders of the visible spectrum can be observed for this grating. So we looked at this 2 different ways in class. One way to do it would be to keep going out, to keep trying new orders, right? To say, well, d sine theta is equal to 3 lambda for red. You could go 4 lambda, 5 lambda, and you keep on going until you can't solve for theta. Right, at some point, this is going to go off the rails. You're not going to be able to fit the diffraction pattern on there. So that's kind of a brute force method. A simpler way to do this would be, let's assume that we're dealing with the far end of the spectrum here, the red light. So assume lambda is 700 nanometers, and let's let theta equal 90 degrees. Okay, so let's find out which order we're at where the angle is 90 degrees. So we're going to set d sine 90 equal to m lambda, and we're going to solve for m. Okay, so m is d times 1, because sine 90 is just 1 divided by lambda. Alright, so m is 2.5 times 10 to the minus 6 over, we're dealing with red light, 700 times 10 to the minus 9. So that's 3.57, okay? So 3.57 orders. That means that it would work for 3 lambda, but if we tried to set d sine theta equal to 4 lambda for red light, it wouldn't work. It would work for blue light, but it wouldn't work for red light. So m equals 3. You basically truncate this and say that 3 complete orders are visible. The other half does not really count there.